We have got traffic lights in our world to coordinate the flow of traffic to ensure that everything runs in a smooth and systematic way. And in the world of electronics, such a powerful device exists as well. It's called a transistor, and it's responsible for controlling the flow of current rather than traffic. But similar to the traffic light, transistors are very efficient in switching and amplifying signals, which is why they're used almost everywhere nowadays. We're going to explore specifically a type of transistor which is called a bipolar junction transistor. It's a fundamental building block that allows hardware to interact with signals like sound and light. This opens up the possibility to control and amplify signals, so I think it's crucial to understand the device from a bottom-up perspective. But of course, there are multiple levels of understanding. At the bottom, we have chemistry, which underpins how charge carriers flow through layers of doped materials. This intimate relationship between holes and electrons governs the behavior of the BJT, kind of like the role gears play in a mechanical clock. I believe having an appreciation of the interaction happening at the atomic level will help to clarify ideas later on. Going up a level, we can build upon the chemistry layer and establish a mathematical basis which engineers can work with easier instead of knowing all the complex chemistry behind it, thereby grasping concepts with graphs instead of equations. We'll have a look at how these graphs encapsulate law and theorems such as the Kirchhoff voltage law, as well as using them to deduce and extract information about circuits in order to visualize the operation of a BJT. Perhaps the most important level is being able to apply these concepts into the real world. For that, I'll introduce an example circuit which utilizes the BJT, coupling it with a photodiode to bridge the gap between the analog signal and the digital interface. With this roadmap set out, we can dive into the chemistry. To put it simply, the BJT has three terminals, namely the collector, emitter and base. For an NPN transistor, the collector and emitter are doped and contain a sea of electrons. However, these two terminals are separated by a depletion layer at the boundary of the PN junction, which prevents charge diffusion. When a collector-emitter voltage is applied, electrons accumulate at the emitter terminal. So far, no current flow has been achieved, but when some voltage is applied at the base, we can see that the negative side of the base voltage supply is depositing more electrons into the emitter. In the meanwhile, more holes have been deposited into the base, signaling a higher demand for electrons to fill the holes. The combined effect of these two actions overcomes the depletion layer at the base emitter junction, and electrons start to enter the base. Some of them will fill in the holes and flow into the base voltage supply, but about 90% of these electrons end up being attracted to the positive side of VCE, flowing into the collector terminal instead. We can look at this in terms of current as well. Since conventional current moves opposite to the flow of electrons, what we have here is a small current flow from the base to the emitter, causing an even larger current flow from collector to emitter. This illustrates the BJT can indeed be used as a current-controlled switch. More importantly, there's a close relationship between the base current and the collector current. Its ratio is known as the beta value, which we'll explore more later on. Moving up a level, we can depict its behavior at different conditions by plotting its response for some given parameters. Looking at the model, we can see that we have a few knobs we can turn to test its response. The first one being the base emitter voltage. Ideally, we would like to know how this base current varies with VBE, because the only way that we can turn on this BJT is to have some sort of base current. So by mapping out the equivalent voltage for any base current, it'll expand our framework so that we can work with voltages as well. Let's take a look at how VBE relates to IB. Doesn't this ring a bell? It is exactly the same as a diode characteristic curve. In fact, this is true because the base emitter is just like a forward bias diode itself. 0.6 volts is sufficient in eliminating the potential barrier between the PN junction, thus allowing base current to flow into the BJT. Referencing to the base characteristic curve, we now have the ability to control the IB by tweaking VBE, which in turn controls the collector current. This is pretty neat. Another dynamic parameter that governs the behavior of the BJT is the collector emitter voltage, setting base current as a controlled variable. Let's vary collector emitter voltage and plot the collector current. There is something really interesting going on here. The collector current remains largely unaffected by the collector emitter voltage for a given base current. The only determining factor of the collector current seems to be just the base current. This makes the BJT an excellent current-controlled current source. Base current is therefore like the handle of a water tap. Adjusting it changes the flow of collector current. At this point, it helps to generalize the behavior of the BJT into 3 different operating modes. Each has a set of voltage parameters. The first one is a cutoff region. When VBE is smaller than 0.6 volt, the PN junction is not being forward biased, so there's no base current flow. Subsequently, this prevents the flow of collector current, so this is analogous to the red traffic light. If we increase the VBE to something above 0.6 volt but limit the VCE to be smaller than VBE, there will be a base current flow in the forward bias junction. However, since the VCE is rather low, the EMF provided by VC is not enough to support a massive current to flow from the collector to the emitter. Although we can still control the collector current by varying the base current, the system has been bottlenecked by VCE. The BJT is therefore in the saturation region, and I think this name illustrates the behavior in this state pretty well. The traffic light has now turned yellow, and current is starting to flow, but at a restricted rate. To turn the traffic light completely to green, all we need to do is to increase the collector emitter voltage so that it's much higher than the base emitter voltage, supplying a bigger EMF to provide the maximum collector current flow at every value of base current. At this moment, the BJT is in the active mode, which is the mode we want to be in if we want to use it as an amplifier. As we change the base current, the collector current changes accordingly irrespective of the collector emitter voltage as long as it's in the active region. If we divide the collector current by the base current, notice that the results for each of these are similar. This ratio is called the current gain ratio, and it is an intrinsic property of the BJT. Typically, the current gain tends to be in the range of 1 to 200, meaning that for every 1 mA applied to the base, we would expect 1 to 200 mA of collector current to flow through. This characteristic is what makes the BJT an amazing component for constructing current amplifiers, as long as we make sure that it's biased correctly to operate in the active region. To summarize these modes of operation, we can use this handy traffic light to illustrate the operating mode we're in, depending on VBE and VCE. If you've picked up all those concepts, you already have a good understanding of this device. To finish off, I would like to illustrate a practical example of how the output characteristic curve can be used to design a current amplifier. Suppose that we want to detect the ambient light intensity to change the brightness of our phone. We can utilize a photodiode for this application. Since photodiode converts light into a small electric current, this small current needs to be amplified into a larger one and preferably be converted to a voltage signal. We can achieve all this by using a current amplifier like this. For this particular photodiode, the typical output current ranges from 5 to 50 microamp under the range of light intensities. Suppose that 10 microamps is the output for the reference light intensity. We can translate this small base current into a larger collector current using a BJT with a current gain of 100. This collector current will then run through a resistor RL for the voltage to be tapped off. There will be a negative correlation between this output voltage and the collector current as stated by this equation. Similarly, since collector current is proportional to base current, a negative correlation can also be found between base current and the output voltage. But you might ask, what value of load resistor would be suitable for input current? Well, there are 2 ways of figuring out. The first one is a mathematical way. If we plot V out against IC, we'll get something like this, with the gradient determined by the value of resistance. Because we're working with 0.5 to 1.5 mA of collector current, we're not going to get the full range of 5 volts when IC changes, but we can live with that. Now, to find RL, we just need to sub in an arbitrary pair V out and IC into the equation and solve for RL. Well, we know that for 1 mA of collector current at the reference light intensity, what we really want the output voltage to be is the midpoint of the available range of voltage, because 1 mA is also the midpoint between 0.5 and 1.5 mA. In doing so, we make sure that the reading on either side of 1 mA can be represented within the available voltage range. Substituting 1 mA into the collector current and 2.5 volt for the voltage output, we get a load resistor value of 2.5 kilo ohms. In this sense, 0.5 and 1.5 mA of collector current will be translated to 1.25 volts and 3.75 volts respectively. Now, this method is well and fine. We've figured out what value of resistance to use, and we can visualize how Vout varies with IC. But at the same time, there's a lot of information that's missing. The most important one being the lack of base current on this graph. Perhaps the question we all need to ask is, how can we know exactly what output voltage would be for any given base current? And if we can visualize the process, that's even better. Fortunately, this can be done. Let's have a look at how we can build upon the first method and extract more information from just one graph. To deduce the value of the load resistor, we start off with some expectation of what the circuit will do, as well as some known facts. We expect the output voltage to be 2.5 volt when base current is 10 microamps, so let's place a dot at this point. Similarly, we also know that when the collector emitter voltage is equal to VCC, in our case 5 volts, there will be no collector current flowing through the load resistor because of the absence of potential difference, so we can place another dot here. Now, if we join these two dots together, we will get a straight line with a y-intercept at 2 milliamps. Notice that Vout is equivalent to VCE, so the voltage on the left of the intersection point equates to Vout, while the voltage on the right represents the PD across the resistor. The sum of these two are always equal to VCC, and we can observe that the x-axis is kind of behaving like a voltage divider. The negative correlation between IB and Vout that we mentioned earlier can also be seen here. As we increase IB, the intersection point shifts to the left, our Vout decreases, leaving a larger PD developed across the resistor. Using the same logic, as IB decreases, Vout increases. In fact, this output characteristic curve has provided us a neat way to visualize Kirchhoff's voltage law in action. Now, to calculate the resistance of the load resistor, we can just divide the voltage across the resistor with the corresponding collector current at the intersection point. Or we can simply use the whole triangle, which is VCC divided by the y-intercept. The magnitude of this straight line's gradient actually illustrates 1 over the load resistor. So it's equally valid to compute the load resistance by finding out the reciprocal of the graph's gradient. With both of these methods, we arrive at the same resistance of 2.5 kilo ohms, but I much prefer the second method as it provides an intuitive way of looking at the response of the whole circuit by just moving some curves and finding out the intersection points. With that being said, let's take this idea a little bit further and look at its response under the same base current exposure with a 5 kilo ohms resistor. A quick sweep across the range reviews just how changing a resistor value can alter the response of the whole system, mapping the base current into a new set of output voltages. To spice things up a little bit, I'm going to track how Vout changes with time when both of these resistors are being exposed to the same sinusoidal base current input, drawing out their paths as they wiggle through time. Putting back into scale, it's interesting to see both of these waveforms represent the input signal without compromising much linearity, but they have also magnified a small base current into a voltage with a larger peak-to-peak output, forming an inverting amplifier with a gain set by the load resistor. As we come towards the end of the video, I would like you to pay attention to the difference between these two waveforms. The 2.5 kilo ohms resistor has been chosen specifically, which means linearity is conserved, and it's very sinusoidal indeed. But what happened to the waveform of the 5 kilo ohms resistor? Although it's sinusoidal, it looks a bit odd, especially with its troughs. Why is this the case? I think this is a question that requires a bit of thought, but if you can figure out the answer, that'll set you up in the good shape to understand concepts such as the DC operating point and biasing of BJT amplifiers. A hint is to look back on the previous scene, specifically at the region that the intersection point is located along the 5 kΩ resistor path when the base current is high. See if you can figure out why. On that note, we've come to the end of this video. If you've learned a thing or two, please click the like button and subscribe to my channel.